In this video we're going to look at the TP line shape. And the idea of a TP line shape is to provide a component within a peak model that represents a general trend in the background signal. In this peak model we've got three components. We've got a bell-shaped curve that represents the photoemission signal. We've also got a component that represents a response of this particular photoemission peak in the background. And then there's the general trend of the background, and it's this general trend in the background that we're trying to model with a component with a line shape that is a TP line shape. TP stands for trapezium or trapezoid, and the basis for this line shape is a trapezium of different left and right heights that are defined by the first and the second parameter that we see here. And while it looks like the left should be half the height of the right, the reason that we have a flat line rather than a steep inclined slope is that the full width half maximum in this case is relatively wide. It's 450 eV. So this change in height is occurring over a large interval, hence we end up with a flat background. And this is part of the fitting process of this trapezium to these data, that the gradient of the top line is determined not just by the relative height we see here, but also the full width half maximum. So the full width half maximum parameter is an important part of fitting a trapezoid line shape to the data. To illustrate these different shapes that are produced from the TP line shape when the first and second parameter are varied, I've created a set of VAMAS blocks from which I've added a component per VAMAS block, so I can display the same component overlaid with these different parameters. And you see the various gradients of lines that are possible when we have an interval that is about 1 eV in width. You just change the display mode so it's clear that we have trapezoids. So if I go to the colors property page and I fill the components, then we can see there is clearly a trapezium here, or a trapezoid. Then the others start but are behind the red one. So if I enable the fill translucent components, we can then see what is behind these various components. So we see all four trapezoid line shapes with these different parameters. And if we go to the second set and just overlay, this is what happens if you reverse the magnitude of the first and the second parameter. You get a declining background shape. So a rising background, in the sense of the binding energy, can be modeled in one way. If it's a declining background in the other sense, then we have the alternative definition of these TP line shapes. So they can be used in both a declining and a rising background scenario to try and model data that is arriving beneath a peak due to inelastic scattering.